Welcome guys, back again to another video. So in this video, let's talk about the jahn distortions. So when we are moving to the video, you need to have the basic knowledge of these things, right? So if you remember, we have complex with cis ligands, so we call it as octahedral complex, right? So when we are looking at the d orbitals of this metal center, there are 5 d orbitals, which are dx squared minus y squared, dz squared, dxy, dyz, and dxz. So when the complex is forming, when the ligands are approaching into the metal center, these ligands are going to separate based on their energies. Two specific orbitals will have occupied the high energies. You need to remember what are these two orbitals, which are dx squared minus y squared and dz squared. And 3 other orbitals are gonna lower its energy, which are dxy, dxz, and dyz. So if you have not have a good idea about how these each orbital oriented around our metal center, I highly recommend you to go to that specific video. I will put the link above. So you need to have a very good idea about that each of these orbitals and how they oriented, how they position around our metal center in order to understand the jahn distortions, right? Okay, so now what is the jahn distortion? Let me take an example and explain it to you. So first let me erase this. There are two types of jahn distortions, right? There are two types of jahn distortions. Okay, now let's move it this way. Okay, there are two types of jahn distortion. The first thing we call as Z in, and other one is Z out, right? So let's talk about the Z in case, right? In this case, I will take an example for copper H2O complex. So here we have a 6 ligand complex, which is octahedral. Okay, now here we have it. Now in the Z in case, right? In the Z in case, what happens is the two ligands, these two ligands over here and over here, these are going come into the metal center, right? These are going to come into the metal center. So you need to feel it, right? When these two ligands come into the metal center, the repulsions between this ligand and this ligand will be increased, right? These 4 ligands have much instability due to the repulsion, because the upper and down ligands are coming together, coming towards the metal center. Due to this effect, what happens is these two ligands are coming towards the metal center and these are going outwards from the metal center. So now we have our ligand complex like this, very shorter bonds with this outer and down, this up and down ligands, and very long bonds with other 4 ligands. This is called the Z in jahn distortion, right? So now you can have the idea about Z out case. So when copper is there, now the opposite thing happens, right? These two are going outwards, this thing goes outwards. Due to this, the repulsions between these ligands and these 4 ligands are decreased. So these 4 ligands are going to come towards the metal center. Now we will have our ligand like this. Hope you got the basic idea of Z in and Z out. But the most main problem is with the jahn distortion is we cannot identify a complex is going with the Z in distortion or Z out distortion. That's a problem with this method, right? but we can tell using this theorem whether the complex is going with either of these distortions, but we can exactly say this is going towards Z in or Z out. That's a problem. So let me go towards the molecular orbital diagram for it. Right, so let me take Z in orientation first. So you know what Z in means, right? Two ligands must come towards the metal center, other four must go far away from the metal center. This is Z in. Now look at this. Now to understand the molecular orbital diagram, you need to have the idea about the orientation of d orbitals around the metal center, right? Okay. Now when these two ligands come towards our metal center, what orbital would be the most affected by it? It should be the dz squared, right? You know, dz squared is oriented just above the metal center, like this. Just like this. Let me take on the color to present that. If you remember, let me take it. Okay, this is dz square, and there's another small ring around this too, right? So this is dz square. Now when these two ligands are coming towards to the metal center, this orbital will be increased its energy because of the destabilization due to the statical hindrance, that electron repulsions, right? So what we have is two energy levels, right? Here we have dx squared minus y squared and dz squared. Here we have dxy, dyz and dxz. But now what happens is, when these two ligands are coming together, coming towards to the metal center, dz squared orbital, here this one, dz squared orbital will unstabilize. It will have a higher energy than this specific orientation. But dx squared minus y squared, look at this, dx squared minus squared, it will be have a lower energy compared to this one. Why? Because these four ligands are going outwards, right? So lower the electron repulsion. So I hope you remember how the dx squared minus y squared oriented around our metal center. It's directly on these bonds. This is dx squared minus y squared. So these ligands are going outwards, which means this dx squared minus y squared are getting released, right? It's getting stabilized. So these two energy orbitals will reoriented like this. Here we have dz squared and here we have dx squared minus y squared, right? So now we have another thing, dxy, dyz and dxz. If you look at the orientations around these 3d orbitals, right, you will see that dxz and yz, they are more affected with these incoming ligands because they are in on the plane, right? Sorry, they are in out of the plane. So I hope you have the 3D picture, right? That's why I have told you, if you have not have the good idea about how these 3D representations work around the metal center, go that video and check it out again, because I have shown it with the pictures and other stuff to explain to you how these 5d orbitals oriented around our metal center. Okay, so if you have the idea, if you have the picture about how these 3d orbitals dxy, dyz, dxz oriented around our metal center, you will see dxz and dyz will have more interaction with these incoming ligands because they are based on the outwards and downwards of the plane. So due to that, these two orbitals will have much effect, much destabilization, cause to increase its energy. Here we have dxy and dyz. y z. Sorry, with this x z. This is z, right? This is z. And dxy is in the plane, right? Dxy is in the plane. These ligands are going outwards, so dxy is relaxed, it's stabilized, it will decrease its energy, dxy. So this is the molecular diagram for Z in distortion. So let me go through with the Z out distortion. It's just the same thing, right? Here now we have longer bonds with up and down and shorter bonds on the plane ligands, right? So here what we have is this one, right? This is the 5 orbitals we have. Here we have dx squared minus y squared, and here we have dz squared, and here we have dxy, dyz, and dxz, right? So when these ligands are going outwards from our metal center, you will see that dz squared orbital, this orbital over here, it will get relaxed, right? Lower electron repulsions because the ligands are moving outwards from it. So dz squared orbital will be relaxed, it will be stabilized, which means it will lower its energy. Lowering the energy means stabilizing. So completely opposite of the Z in distortions, dz squared will be stabilized, dx squared minus y squared will be unstabilized, which means increasing its energy. Same thing happens over here. Now dxy will be unstabilized, other two will be stabilized. So this is the molecular orbital diagram for Z out distortions, right? Now you have the basic idea about what is this Jahn-Taylor distortion all about. Now let's see some examples, like how we can determine whether the distortions happens or not, right? These distortions are based on the symmetry, right? So what these distortions are all about? Jahn-Taylor distortion. Jahn-Taylor distortion is all about to interrupt the symmetry of your complex, right? Interrupt the symmetry of your d orbitals and then give some additional stability towards your ligand, to your complex, right? Let's say like this. Now we have an electron configuration like this, right? Let's say like this. Okay, now what's happened is, we can calculate the stabilization energy based on the crystal field theory, right? So what this Jahn-Taylor distortion is all about is, if you can determine a unsymmetry around the degenerate orbital level, I will explain it using an example, right? If you can determine an unsymmetry around the degenerate orbital level, then this Jahn-Taylor distortion is all about to make it more stable, right? So what is it mean by this unsymmetry? Like now you need to consider two aspects, this EG level and T2G level. First, let's look at the T2G level. Is this T2G level symmetry or unsymmetric? This is unsymmetric, right? Here, this have a 2, this is 1 electron. This is unsymmetric. If we have it like this one, this is perfectly symmetric. This is perfectly symmetric. So this Jahn-Taylor distortions occurs only on unsymmetric systems, not on symmetric systems. So in this case, Jahn-Taylor distortion won't be happen. So in this T2G case, this is unsymmetric. Let's take about the EG state. It's symmetric, right? Both the orbitals have an electron, so it's completely symmetric. So in this case, in this particular orbital, in this particular electron configuration, we can observe a weak Jahn-Taylor distortion. Here we have a weak Jahn-Taylor distortion. Why we are calling this a weak Jahn-Taylor distortion? Right? It's based on this T2G level. If your T2G level is unsymmetric, if your Jahn-Taylor distortion is all about the T2G level, you know that for symmetric systems, Jahn-Taylor distortion won't occur. Jahn-Taylor distortion will occur only on unsymmetric positions. So if your unsymmetric state, if your unsymmetric degenerate state is T2G, then it's a weak Jahn-Taylor distortion, right? Let me take another example. We have an electron configuration like this. What we can tell about this, right? What we can tell about this one? So we have two aspects, T2G level and EG level. First, what you have to do is you need to consider both these two degenerate states individually and check whether these are affected by the Jahn-Taylor distortion. How we can determine it by checking the symmetry. Here T2G level, it's perfectly symmetrical, so this has no Jahn-Taylor effect, this type, right? But this case here, EG level is unsymmetric, which means there is Jahn-Taylor effect. So overall, our complex contains Jahn-Taylor distortion, strong Jahn-Taylor distortion. Why? Now this unsymmetry is all about the EG state, which is the dominant. In Jahn-Taylor distortions, this EG state's unsymmetry is dominant, right? If you have an unsymmetry in T2G state, it's not that much effective, but we call it a Jahn-Taylor distortion, but it's a weak. If you have a symmetry on EG state, if you have an unsymmetry, this one, unsymmetry on EG state, which means it's a dominant Jahn-Taylor distortion, we call that strong Jahn-Taylor distortion. Very good. So I hope you got the idea. So let me do a simple example. So take some time and do this example. So here's the problem. We have no, not a cobalt. Let's say cobalt H2O. No, let's say like this one, Ml6. This M is a metal center which has the electron configurations of 3d5 4s2. So I'm telling you this complex is weak field ligand. This complex is a weak field. Now I'm asking you whether this complex contains strong Jahn-Taylor distortion or weak Jahn-Taylor distortion. So pause the video and try the example. Okay, now let's try this. So you know we have in the octahedral geometry, we have 5 electrons, right? We have 5 electrons in the d orbital. So let's put it on here, 1 2 3. Now there's a problem, right? Here now we need to check whether the next electron is go either this way or this way. That's why this option is there. This is a weak field ligand. Weak field means this gap is lower, so our electron can quickly jump to here. 1 2. Now to check whether this contains Jahn-Taylor distortion, look at the T2G level, it's perfectly symmetric. Look at the EG level, it's symmetric, right? So both are symmetric, so no Jahn-Taylor effect. No Jahn-Taylor distortion. So this is completely fine, right? I hope you got the idea about it. So if you draw all the configurations, molecular orbital configurations for D1, D2, D3, D4, D5, like D4 in high spin and low spin, D5 in high spin and low spin, you can completely identify whether each of these are showing the Jahn-Taylor distortions or not. You just have to draw the molecular orbital picture with electron configurations just like this one, then find out each of the T2G and AG level whether symmetric or not. If it's symmetric, that particular degenerate level doesn't show the Jahn-Taylor distortion. If it's unsymmetric, then it shows the Jahn-Taylor distortion. If this unsymmetry is all about the EG state, right? Is this all about the EG state? Then it's a strong Jahn-Taylor distortion. If this unsymmetry is all about the T2G state, it's about the weak Jahn-Taylor distortion. So I hope you got the idea about the Jahn-Taylor distortions. So in the next video, we'll talk more about the complexes and its energies.